The next part we're going to move on to now are standing sound waves. So we'll stick with standing waves, but now we'll apply it to a sound wave. So just as a reminder before we get started, sound waves are longitudinal waves in air. Let's just show a demo of it. So we studied in the last chapter that sound waves are produced by a source and they're spread by the motion of the air molecules. Where the air molecules are closely packed together, they have high pressure relative to equilibrium. That's called a compression. Where the air molecules are spread out, they have low pressure relative to equilibrium, and that's a rarefaction. Okay, we're going to build on that idea and come to standing waves. Next, let's ask what happens if the sound is in a tube or a closed container. You can completely have this. It happens all the time if you blow across the top of a pop bottle or a water bottle. When you blow across the top, sound goes in the part of the bottle that's filled with the air, so the top portion of the bottle. It moves through the air and it hits the surface of the pop or the water. That's a closed end. That's a fixed barrier. So what happens to the sound and what happens in particular to the air molecules at the barrier? What you see on the screen now is a simulation. It's developed by Dan Russell at Penn State. He's got a really super website with a lot of good visualization of waves, so I recommend it if you're looking for something to help you see this. So what we have here is that the waves come in from the left, they travel to the right, and they bounce off the end. Then, just like our waves on the string, the reflected waves and the incident waves interfere. When you have the right conditions, you get standing waves in air, just like we get standing waves on a string. If you want to apply this to the idea of blowing across your pop bottle, your standing waves are occurring when your bottle really hums loud, when it really rings out. So that's how you know you have the standing waves. So our standing waves in air are the alternating regions of compressions and rarefactions, and that's what a standing wave in air looks like. So for our next bit, let's start to describe what happens to the air molecules. What's the motion of the air molecules look like? So let's start by looking at the motion at the right end of the tube. So on the right end of the tube, so right here, the air molecules right here, they don't move at all. So with regards to motion, this is called a node, and in particular, it's called a displacement node. When we have our standing waves, there are other regions also where the air molecules don't move at all. So about right here, they don't move. Where else don't they move? They're not moving much at all right here. They're not moving right here. A little bit hard to draw, but I'm trying my best. I'm trying to pick the spots where they're not moving. So there are regularly spaced regions where the air molecules don't move. So those are the displacement nodes of the standing nodes. Those are the displacement nodes of the standing waves. In between the nodes, we have the areas where the air molecules are moving the most. So let's find some of those spots. Right here it's moving a lot, here it's moving a lot, and here it's moving a lot. Where it's moving the most, those are our displacement antinodes. So we can label those with an A for antinode. And our nodes we can label with an N for node. So node, node. So our standing waves with our areas of compressions and rarefactions, those lead to displacement nodes and antinodes. And we often use what we see here in the lower graph as a way to visualize that. So this is just a graph of the displacement of the air molecules. And of course, this is a live one, so it's happening over time. Yeah, and on this graph, we can see the nodes and the antinodes. So the nodes and antinodes happen on this graph too. Okay, so this is just a way to plot this. This one the one in the middle is easier to draw than the one on the top. So that's where we talk about the motion of the air molecules. Next, we'll talk about pressure. Pressure is probably the more physically accurate way to think about standing sound waves. And that's because a sound wave really is a longitudinal wave in the pressure variation of air, where it's measured relative to an equilibrium pressure. So here in our slide, our top picture is showing the motion of all the molecules over time. The middle picture is showing the displacement of the air molecules. Some places, like at the very end, they don't move at all. Some places they move the most, so we go between nodes and antinodes. And then our bottom picture is now talking about pressure. So let's look at the closed end of the tube again. So let's look at this portion of the tube. And what do we see happens right here? We already established that those air molecules don't move at all. That's why it's a displacement node. But if we look at the neighbors, sometimes they're all crammed up together and sometimes they're spread out. So it alternates between being highly compressed and highly spread out. That would correspond to a pressure antinode. So right here we get a pressure antinode because it varies between spread out and close together. And that happens at other places as well. If we look right here, this one is really dramatic. It varies a lot. So the molecules right in the middle, they don't move at all, but the neighbors sure do move a lot. So we have a displacement node, and we get a pressure antinode. And then that happens again right here. Whoops, my line went a little bit squiggly. And it happens right here. And it happens right here. Okay, so all these places show pressure antinodes because we get the maximum variation in pressure relative to the equilibrium. So what about the other extreme? In between the pressure antinodes, we have places where the molecules all have the same relative packing. So it's always about the same amount. So they all move together, so they don't get more squished together or more spread out. So we get a displacement antinode because they are moving a lot, but the relative pressure doesn't change. That means we get a pressure node. And that happens at all the places that look like that. So if we wanted to, we can draw pictures of the displacement of the air molecules. That's our displacement picture in the middle. Or we could also draw the pressure in the tube. So the pressure description is also a very good description of these waves in the tube. So what we take away from this is that our sound waves can make standing waves. One of our boundary conditions is that at the closed end, the air molecules don't move at all. We get a displacement node and a pressure antinode. And at other places, the air molecules do move quite a lot. There we have displacement antinodes and pressure nodes. When we compare our displacement and our pressure pictures, we see that they're exactly opposite. So they're out of phase.